Assalamu alaikum dear students. I welcome you to 33rd lecture of probability and stochastic processes. In last lecture we finished the study of probability theory, and from today we are going to start our discussion of stochastic processes. When I say we finished the study of probability theory, please do not assume that we are not going to see probability theory for rest of the lectures in this course. On the contrary, we are going to see the principles we have learned play an important role in analysis of the problems that we are going to discuss in coming lectures. What I wanted to say was that we finished the study of fundamental principles of probability theory, and we are going to work on advanced problems where probability theory will be used to analyze these advanced problems. We are going to start the study of stochastic processes today. Before formally starting the discussion of stochastic processes, let's review what we learned in the last lecture when we were discussing convergence of a sequence of random variables. We'll try to connect the idea of convergence of a sequence of random variable to the idea of a stochastic processes. We discussed the idea of convergence of a sequence of random variables in context of population sampling, where we had a huge population and we picked samples from that population and found the average value of a quantity of interest that we measure on all the individuals of the sample, and try to estimate a parameter that modeled the probabilistic behavior of the whole population. Imagine you are applying this principle of population sampling to estimate the average height of a male student at a large university. So you start with a reasonably large sample of 10 students. You pick 10 random students, measure their heights, find the average, and keep this as your value of 10th random variable. Then you increase the sample size by 1, take 11 students, measure their heights, find the new value of sample average. As you keep on increasing the sample size and get new and new values of sample average, this sequence of values of sample average will vary slightly from previous value to the next value. And by laws of large numbers, we know that this sample average of progressively larger and larger samples is going to converge to population mean. In this case, we are perhaps only interested in estimating the population mean, so we'll be just observing the sample mean and keeping that as a record and see if the observed values of larger and larger samples converge to a value or not. We might be interested in some other observations while we are doing this, while we are taking larger and larger samples and taking their average. Perhaps not. But I'll give you another example where you will certainly be interested in other than the sample average. Suppose you have 100 rupees and you go to a gambling house, not in this country though, but somewhere else, and you start gambling. The game that you play is a simple coin toss based game where the dealer will toss a coin, you will call a head or tail, and if the coin stops with your called side on top, you will win 1 rupee. Otherwise, you will lose 1 rupee. So you start with 100 rupees and you keep on playing and playing and playing, and we are interested in your net holding, your net possessions as the game goes on. Here we are working with a sequence of random variables. What are they? They are the outcomes of coin tosses. The first coin toss gives you the outcome of first random variable capital X1. The second coin toss is the outcome of the second random variable capital X2, and so on. So there is a collection of random variables which are the outcomes of coin tosses. But we are not interested in outcomes, their collection, their average value. We are interested in the total sum, the total holdings, the total possessions, which can be obtained by this formula: 100 plus capital X1 plus capital X2 plus capital X3, and so on. So if you have played the game for capital N times, then your total holdings are 100 plus capital X1 plus capital X2 plus capital X capital N. Assuming that capital Xn, the fundamental random variable, takes only two values. If you win, it takes a value of +1, and if you lose, it takes a value of -1. So your total holdings after capital N games is 100 plus capital X1 plus capital X2 plus all the way to capital Xn. If you continue to play and the game goes on for hours and hours, then we might be interested in some other interesting observations. For example, if you have started with 100 rupees, what is the probability that you have doubled your possessions to 200 rupees? Or if you are not so lucky, what's the probability that your net possessions have gone to half of what you started with, that is 50 rupees? And if it is totally not your day, you might go bankrupt. So what's the probability that you start with 100 rupees, play a sequence of fair coin toss type games, and end up bankrupt, lose all of your 100 rupees. So in this type of a situation, we are not interested in convergence of a random variable or convergence of a sequence of random variables. We are interested in a quantity, the value of a quantity which depends on a collection of random variables, and we want to see where the value of that quantity of interest goes as the game goes on. In this example of gambling based on a fair coin toss type of game, the underlying random variables are capital Xn, the outcomes of coin tosses, and the quantity of interest is capital Yn, where Yn is equal to our total holdings after n rounds of fair game has been played. So as the game goes on, this Yn varies in an unpredictable manner. You cannot predict what will be your holdings after 200 rounds of this type of fair game. But you know that there is a sense of time associated with it. This quantity, your net holdings, vary with time. As the game is played, it goes up or goes down in an unpredictable manner. So a quantity which varies in an unpredictable way and it has a sense of time associated with it is called a stochastic process. And a stochastic process can be modeled by a collection of random variables. So if a stochastic process or a time varying unpredictable quantity varies at discrete instances of time, t1, t2, t3, and so on, then this type of stochastic process is called discrete time stochastic process or discrete parameter stochastic process, because it changes its value at a few discrete instances of time. These discrete instances of time can be finite or can be countably infinite. Furthermore, these instances of time when the stochastic process changes its value, t1, t2, t3, and so on, do not have to be equispaced. The distance from t1 to t2 can be different from the distance from t2 to t3, and so on. If an unpredictable quantity that varies with time varies continuously, then it's called continuous time or continuous parameter stochastic processes. There are many examples of such stochastic processes. For example, the atmospheric pressure or temperature, or any other quantity that is controlled by many unpredictable forces of nature. And if such a quantity varies continuously as a function of time, it is called continuous time or continuous parameter stochastic process. In the case of gambling, our total winnings were discrete time stochastic process, and such stochastic processes are represented by capital letters with an index of n, where n is the instance, the time instance where the stochastic process changes its value. On the other hand, if a stochastic process is a continuous time or continuous parameter stochastic process, it is represented by a capital letter x, y or z with an index t. So this index t represents the parameter which parameterizes this value which varies in an unpredictable manner. As I said, a discrete time stochastic process can be modeled with a finite or countably infinite collection of random variables. Whenever a discrete time stochastic process changes its value to an unpredictable new value, that unpredictable new value can be thought of as a new random variable. So you need a finite or countably infinite number of random variables to model a discrete time stochastic process. But to model a continuous time stochastic process, you need an uncountably infinite collection of random variables, and this collection is parameterized by continuous parameter t. We'll talk more about continuous time stochastic processes towards the end of this course, but today we are going to start with Markov chains. Markov chains are example of a discrete time stochastic process. Not only that, it is a special type of discrete time stochastic process where the values that the random variables are going to assume are also discrete, could be finite, could be countably infinite, but they are also discrete. So if we have a collection of finite or countably infinite number of random variables where these random variables take on values from a set which has finite or countably infinite values, we can have a Markov chain. Every such stochastic process is not Markov chain because Markov chains have some special constraints, and we are going to talk about them. So let's formally start our discussion of a Markov chain. A Markov chain is a discrete time stochastic process which takes on values in a finite or countably infinite set. This set is called state space. The values that we are interested in, the values that we observe, the whole collection is called a state space. So a quantity of interest varies, changes its value in an unpredictable manner and takes on values in a set called state space. The values that change from one state to another happen at discrete times, t1, t2, t3 and so on. If the value of interest at time instance tn is represented by a random variable capital Xn, then this random variable is a discrete random variable because it takes on values in a discrete, finite or countably infinite set. So we have a collection of discrete random variables which are used to model this stochastic process called Markov chain. So we have an infinite collection of random variables which need to be analyzed so that we can analyze the behavior of this stochastic process called Markov chain. But analysis of a possibly infinite collection of random variables is going to be quite complex. So we are going to put some restrictions on their mutual interdependence. The simplest restriction is that all these random variables are independent of each other. We can also put a similar restriction on the values of stochastic process, the values of Markov chain that it assumes as the time goes along. But if we put such a strong restriction, then the resulting stochastic process is not very interesting to analyze, because we know that if a quantity is varying in an unpredictable manner, then knowing the current value of this quantity will not allow us to accurately predict its future values, but knowing the current value is going to affect the range of possible future values. For example, if you are talking about your total winnings at a certain time, when you have played the game for a few hours, suppose your total winnings are 235 rupees. Knowing this, you can tell that in next 10 or 15 minutes, your total possessions will be close to this value. They will be in the range of say 260 from top to 210 from bottom. They will not be 0 or 50 or 100, provided that in next 15 minutes the number of rounds that can be played are from 10 to 20. So knowing the current value of an unpredictable quantity gives you some idea of the range of the values that the future values are going to assume, but it does not give you the exact value that the future values will have. So you cannot put this restriction of total independence of the values that a stochastic process assumes. So there are going to be some interdependence. A Markov chain is a special stochastic process where if you know the value of the stochastic process at this time, you don't need to know how it reached here now. The stochastic process could have reached at this state at this time through many paths, but as long as you know its current value at current time, that's all you need to know for predicting in a probabilistic manner, for predicting the future values, the range of future values. So if the future values depend on the current value and not the values before current value, such a stochastic process is called Markov chain. And this property is called Markov property, where the current value of the stochastic process encapsulates the whole history of the past behavior. Knowing the current value is enough to work with the probabilities of future values that the stochastic process is going to assume. Our example of gambling, which starts with 100 rupees, is an example of stochastic process. And as you play along, you get different values of your total possessions. After the first round, your total possessions could be 101 rupees or 99 rupees. After 2 rounds, your total possessions could be 102 rupees or 100 rupees. If you win both times, it is 102 rupees. If you win and lose, then it is 100 rupees. It could be 98 rupees because you lost both of the rounds played. Or it could be 100 again if you lost one round and won the next. So after 2 rounds, the possible values are 98, 100 and 102. As you keep on playing round after round, your total possessions will be varying in an unpredictable manner. But if you know your current possessions, say 235, then you know what are going to be the possible values of next possessions. It will be either 236 if you win or 234 if you lose. So as you play, your total possessions move from one state to other. They move up or they move down depending on the fact that you win or you lose. So this transition from one state to another is usually shown in a state transition diagram. Let's have a look at one such state transition diagram. Here the state is random variable capital Yn, which is 100 plus x1 plus x2 plus all the way to capital Xn, where Xn is the random variable representing the winning of $1 or 1 rupee or loss of 1 rupee for each round. So if you have played n rounds, your total possessions are this. And if you start with 100, if you win, you move to 101. If you win in the next round, you move to 102. If you lose, you move back. If you lose, you move back. And if you continue to lose, your possessions will become less than 100. So this is the kind of state transition diagram for the example of gambling using a simple game of coin toss, where your winning can be 1 rupee or your losses can be 1 rupee after each round is played, and this transition takes place after every round. This state transition diagram can go on towards positive infinity in this manner. But what happens when you move closer to 0? If you look carefully, if you have lost almost everything and you are on the verge of bankruptcy, say you have only 2 rupees, you lose one more, you will move to 1 rupee. It is quite possible that this last 1 rupee is very lucky for you and you start winning and going forward, but it's possible that you lose your last 1 rupee and reach a state of 0, a state of bankruptcy. From here, you cannot move anywhere. Now this stochastic process has ended at a state which is not going to allow the stochastic process to change further. This state is called an absorbing state. All other states have similar characteristics, but this state of having 0 rupees or being bankrupt is a special state. It is called absorbing state, and once you reach there, you cannot get out. The stochastic process stops. So this type of unpredictable time-varying quantity, which varies at discrete instances of time with special characteristics, that if you know the current value, that is all you need to know to predict or to work with future values, and you don't need to know the past behavior. This type of stochastic process is called a Markov chain. Let's look at another example of a simple Markov chain. Here we have a device, a machine, an electronic or mechanical, any type of machinery which has a tendency to break down, go out of order, and then it is repairable. So it can be found in 2 states, working or non-working. Suppose we check the status of this machine or device every morning. So if this morning it is working, then it has some probability, non-zero, of being in a state which is not working next morning. So we check this device every morning, and if it is working this morning, it may be working next morning or it may not be. So there is a probability P that it will not be working, and probability 1 minus P that it will still be working when we come next morning and check its status. Now suppose this machine is not working. When we checked it this morning, it's not working. Then its repair procedure is so simple that it is definitely going to be repaired and it will be working condition next morning. So when it is not working, the next state is always working. But when it is working, it is possible that the next state is working, still working, or it could have gone out of order and it's not working. So there are only 2 states. Let's call state of not working 0 and state of in perfect working order 1. So these are the labels 0 and 1 which we assign to the 2 states that this device could be found. And there are associated transition probabilities. transition from working to not working and transition from not working to working. There is another transition which is not really a transition, from working to working. Nothing changes, but there is an associated probability, an associated transition from working to again being found in working order. So all these transitions, their associated probabilities, their transition diagram can be simply shown with two states. For this simple example of two states and associated transition probabilities, we have the state transition diagram here. So state 0 is where machine is not working, state 1 is where machine is working. And there is a probability P associated with this transition from working to not working. So if it is working this morning, there is a probability P that it will go out of order by next morning. And there is a probability of 1 associated with this transition. If it is found to be not working at a certain instance of time, at a certain morning, the next morning it is definitely going to be in a working condition. And here is the transition, the dummy transition, where it is working at this instance of observation, and the next instance of observation also gives this machine in a working state. So this is a simple stochastic process, a simple Markov chain with two states and associated transition probabilities. We are going to analyze this simple case in greater detail towards the end of the lecture. But let's look at a slight variation of this two-state mechanical or electronic device that is repairable and it has a tendency to fail. This state transition diagram is very similar to the case that we just discussed. The only difference is that once the machine has gone out of order, you can have it repaired by the next morning with a probability Q, and there is an associated probability 1 minus Q that machine will not be repaired in one day. If you want to make this stochastic process a Markov chain, then you cannot have a memory. That is, if technicians were trying to repair it and they could not repair it in one day, then they lose all memory of their work by the next morning. And by next morning they have to start afresh. This is necessary because in Markov chain, once you are in a state, say state 0, you do not need to know how you reach there. You do not need to know the history of your travel before you reached here. So suppose you are at state 0, machine is not working and technicians are going to start their work early in the morning. They should not have any information whether they have spent 1, 2, 3, 4 or 5 days repairing this machine already. Their work should be started from the beginning. This is just like the movie 50 First Dates, where Adam Sandler looks so unnatural trying to play a serious role. Please do see that movie. There is an interesting characteristics of these transition probabilities of Markov chain. If you look at this diagram of state transitions, you will see that once you are in state 1, there are two paths that you can go out. So a random variable takes on its value, and as a result of that value, the state changes. The state of this Markov chain changes, and from this state, it can either go to this path to 0 state, or it can remain at one state by following this path. So this collection of all possible states which can be reached from this state represent a total sample space of the underlying random experiment. So probabilities associated with these outgoing branches should add up to 1. So for any state, if you add up all the probabilities associated with outgoing branches, this 1 minus P and P, they should sum up to be 1. Similarly, from state 0, all outgoing branches have probabilities of 1 minus Q and Q, and they should also sum up to be 1. The next example of Markov chain is more complicated than this simple two-state Markov chain, and this captures the idea of total number of descendants of a famous historic personality. So if you count the number of descendants on first day of year every year, then from year to year the total number of descendants could increase or decrease. So if more children were born into that tribe than the people who died, then the total number will jump by 1, 2, 3 or even more. And if for some unfortunate reason more people died than the number of children born, then the total number of descendants will decrease by a value of 1, 2, 3 or more. So the jumps can be more than one on either direction, towards positive side or negative side. So this is a complicated Markov chain, and we are going to show only the state transition diagram for just one node. So if this is the node of interest, then there will be many arrows coming here and many arrows leaving this, but we are only showing the transitions going out of this node. So at the first day of this year, if this was the number of descendants, then on the first day of next year, the number of descendants could be 1 more, 2 more, 3, 4, or even by a larger number. Similarly, it is possible that the number of descendants could have reduced by 1, by 2, 3, 4, or even a larger number. So this is a complicated state transition diagram that you just saw, and this represents the total number of descendants of some famous historic personality. We are not going to analyze this complicated Markov chain, and we'll move to our next example, which is simpler than this, and we might analyze this time permitting. This particular example is about the status of a Pakistani Muslim who wishes to perform Hajj. Based on his circumstances, his status could be in one of many states. The first state is where he is just thinking about it and he has not formally applied for Hajj. And if he has applied, then his status moves to the next state where his application is under process. It is being reviewed. So suppose his application is reviewed and it is accepted for a random draw, which usually takes place because number of applicants is much larger than the number of slots available for Pakistani Hujjaj. I'm not talking about that case where there are special tour operators, Hajj operators, who can take you whenever you want to perform Hajj because they have obtained some special quota because of their financial resources or because of the strength of their contacts in the Ministry of Religious Affairs. They can take you to Hajj whenever you want it, of course at a higher price. I'm talking about an average Pakistani who has to go through the regular channel where his application is put together with other applications and a random draw takes place to select the number of applicants against the number of available vacancies. So if his application is accepted for random draw, his status moves to next state. And if his application is accepted, it comes out in that random draw and he is allowed to go to Hajj, then his status moves to next state. And most probably from that state, he is going to perform Hajj and become a Haji. The rest is not to be discussed in this course. So this unpredictable quantity, which is the status of an average Pakistani Muslim who wishes to perform Hajj, is a Markov chain. And let's have a look at its state transition diagram. We'll start with this. This is a state where he's thinking about performing Hajj. He's trying to gather his financial resources, and this transition means that 1 year passes and he still does not apply. Another year may pass and he still does not apply for the Hajj. And once he applies, his status moves to the next state where his application is under process. And if in the result of random draw his application is selected, he goes to this state. And from this state, he is going to perform Hajj by going to this state. This is the state where he has performed Hajj. And from this state, it never goes out unless he performs a second or third Hajj. One is necessary. So after performing one Hajj, his state remains here. He is a Haji now. You might question this arrow, which means that once his application is approved, he does not go to perform Hajj, but remains in this state where his application is under process. This represents some unforeseen circumstances where he has to postpone his desire to perform Hajj. But this is a general state transition diagram of an average Pakistani Muslim who wishes to perform Hajj. We have not assigned transition probabilities to any of the transitions. Let's assign a typical value to each transition probability. Suppose once he is in state 0 where he is thinking about performing Hajj, there is a 90% chance that he still cannot collect all the financial resources to go for Hajj, and he remains in this state year after year. So there is 10% chance that in any year he is going to apply for Hajj. So this 0.9 and 0.1 is going to give us a total outgoing probability of 1. Once his application is here, there is a 60% chance that his name will come up in a draw, because usually the number of applicants are 60-70% higher than the available vacancies. So there is a 60% chance that he will get an opportunity to perform Hajj, and there is a 40% chance that he will go back where he has to apply again. Once he is here, there is a very strong 99% probability that he will actually perform Hajj, and there is a very minor 0.01 probability, 1% chance that he may not perform Hajj, even his application is accepted. And once he has performed Hajj with probability 1, he is going to stay in this state. We are not going to analyze this problem now, but we might do that in a later lecture. But this is a general transition diagram where the rightmost state is once again an absorbing state. Now that we have looked at a few examples of Markov chains, let's analyze one particular Markov chain in greater detail. The Markov chain that we are going to analyze in greater detail is the simple case of a machine or device which has a tendency to fail, but it is repairable, and it is repaired very quickly in just one transition because the repair mechanism is very simple. So this simple two-state Markov chain will be analyzed in greater detail. Let's have a look at its state transition diagram, which is shown on your screen, and we are also seeing the state transition probabilities. A state transition probability is usually written with a P and then two parameters. The first parameter is the initial state of the Markov chain, and the second parameter is the next state. So P1,1 is the state transition probability of this Markov chain moving from state 1 back to state 1, which is 1 minus P. Similarly, state transition probability P01 is the probability of this Markov chain moving from state 0 to 1, which is 1, because when it is in state 0, the machine gets repaired immediately, and by next morning it is in working order. P1,0, the state transition probability from working condition to going out of order, is P. We are going to use all these state transition probabilities 1 minus P, 1 and P. We have not listed state transition probability for 0,0 because that is 0. Once the machine is in an out of order condition, it does not remain there at all. It moves to working condition immediately. There are two other things need to know. They are the initial probabilities. We have assumed that on the first day before this Markov chain starts taking on its values, the machine is in working condition. So by developing a general formula and changing it into a recursive formula and then starting from state 0, we have found the probabilities of this simple two-state Markov chain being in state 0 or state 1 at nth sampling instance. And these formulas convey a lot of information. So we might be interested in finding the probability of this Markov chain being in state 1, that is in working condition, on 10th day of its observation. Or we might be interested in its asymptotic behavior. What's the probability of this Markov chain being in state 1 asymptotically large values of t, time? So what is the probability of this Markov chain being in state 0 or 1 once it has gone for many transitions? We can find all these probabilities if we analyze the behavior of this Markov chain using the initial probabilities pi 0, pi 1 and the state transition probabilities. Let's try to find these probabilities of this Markov chain having been in a certain state on a certain day. For this simple two-state Markov chain, we are going to find probability of this Markov chain being in a certain state on a certain transition time. So we are going to find the probability of xn plus 1 being equal to 0. Since this is a Markov chain, all we need to know is where this Markov chain is at previous sampling time when we are looking at capital Xn. It can be at 0 or it can be at state 1. So probability of xn plus 1 being 0 is equal to sum of two probabilities. First is that the previous state is 0 and it remains at 0, and this is transition probability 0, 0. The next is probability of this being at state 1 and then moving to state 0, and this is transition probability of 1, 0. If you put values of these probabilities and transition probabilities, you will find that probability of xn plus 1 being 0 is probability of previous state being 0 multiplied by transition probability from 0 to 0 plus probability of previous state being 1 multiplied by transition probability from 1 to 0. If you put values of these transition probabilities and keep these expressions as they are, you will see that probability from 0 to 0, the transition probability from 0 to 0 is 0. So this expression goes away and you are left with this probability being equal to probability of xn, the previous state being 1 multiplied by transition probability from 1 to 0. We want to express this probability of xn plus 1 being 0 in terms of previous state also being 0. But this is previous state being 1. If probability of previous state being 1 is known, then probability of previous state being 0 is just 1 minus that probability. So this probability is equal to this probability. So this gives us a recursive formula for probability of xn plus 1 being equal to 0 is equal to 1 minus probability of previous state being 0 whole multiplied with p. We are going to use this recursive formula to find different probabilities. First, we'll find probability of x1 being equal to 0. You plug in the required values and it comes out to be 1 minus pi 0. This is the starting probability. So if you have this starting probability of being in state 0, you use that to find the probability of x1 is equal to 0, and it comes out to be p minus p times pi of 0. You use this in that recursive formula to find probability of x2 being equal to 0. You plug in all the numbers and you get this expression p minus p square plus p square times pi 0. Similarly, probability of x3 being equal to 0 is a more complicated formula, slightly longer, p minus p square plus p cube minus p cube times pi 0. And I hope you can see a general structure here. For any nth state being in state 0 is equal to minus p whole raised to power n into pi 0. This is the general expression for this. And there is a summation of p minus p square plus p cube, etc. And this has been compactly written as p times the summation from k is equal to 0 to n minus 1 of minus p whole raised to power k. So this is the formula for probability of xn being in 0 state. If you look at this formula, particularly the second part, this is just summation of geometric series. We are going to use the formula for summation of this geometric series to simplify this expression. If we use that formula, which is shown here in square brackets, we get this expression. And if we simplify this expression, we get a formula for probability of xn being in state 0 to be p over 1 plus p plus minus p whole raised to power n multiplied with pi of 0 minus p over 1 plus p. If we take the other probability of xn being in state 1 and simplify its expression, we get an expression which is similar to probability of xn being in state 0, except for a few differences. Instead of p, we have 1 here. Similarly, instead of p, we have 1 here. And instead of pi of 0, we have pi of 1. So this general expression is for nth random variable xn to be in state 0. And this expression is for nth random variable xn to be in state 1. So by developing a general formula and changing it into a recursive formula and then starting from state 0, we have found the probabilities of this simple two-state Markov chain being in state 0 or state 1 at nth sampling instance. And these formulas convey a lot of information. One piece of information is the asymptotic behavior of this chain. What happens to probability of this Markov chain being in state 0 or state 1 when n goes to infinity? All you have to do is see how these formulas behave when n goes towards infinity. There is only one expression which involves n, and that has minus p raised to power n. P here is one of the transition probabilities. If this transition probability is a number less than 1, then this whole thing is going to converge to 0 in an oscillatory manner, positive, negative, but these numbers are going to be smaller and smaller and smaller, and they will approach 0. When this approaches 0, this whole expression vanishes. So asymptotic probability of this Markov chain being in state 0 is 1 over 1 plus p. Similarly, asymptotic behavior of this Markov chain being in state 1 is p over 1 plus p, because this whole expression just vanishes away. With this, we conclude our analysis of this simple case of two-state Markov chain. The other variation where there was a state transition probability q involved, which was the probability of machine getting repaired in 1 day, has been left as a homework. You should look at that two-state Markov chain, look at its transition probabilities, look at starting probabilities, and derive a general recursive formula to reach these formulas. These formulas are a special subcase of that formula where the transition probability Q becomes 1. You are going to analyze the case for a general value of Q. Starting with next lecture, we are going to analyze other Markov chains and look at more properties and characteristics of Markov chain. Till then, I wish you the best. Thank you. Khuda Hafiz.